I hope this is true. I think that's how we got the n+1 policy, was by performing this minimization, right? Yeah? Okay. What if we say, well, forget about minimization. Let's stick in the last policy. You can always have fun. And remember, that's in my notation. This is just C of x. Excuse me. Okay. Everybody with me there? Yep. All right, so I have this is equal to this minimum. And the n+1 means that the minimum, the minimum was phi n+1. But let's say phi n+1 is optimal. I'm putting a suboptimal policy, which is phi n of x. Okay? And my notation was that is what I defined to be Cn of x, and that's what I defined to be Pn. Now what's that? Poisson? Or in French, poisson. So this is equal to Hn of x. Right? And what is that? So you end up with Pn+1, Hn is less than or equal to Hn minus Cn+1. Oh, wait. Minus Cn+1. That, I put that to the other side. That's there, and then plus Hn. So Hn serves as a Lyapunov function for the n+1 policy. Now, if I'm in a finite state space setting, I can always just add a constant. I can assume Hn's positive, all right? It doesn't matter. I can always add a constant and make it positive. So Hn serves as a Lyapunov function. I know the indices are a bit confusing, but we have an inequality because of this putting in the wrong policy here. And that's it. So basically, you all know that if you have Poisson's inequality holding, then the steady state cost for this new guy, which I call 8n+1, is less than 8n. So that's it. Okay. Cool. And the fact that it turns out if it was ever strict, it would stop. The algorithm would stop, and you'd be data star. So when as soon as you get equality, you've stopped. It's optimal. Yeah, in the finite state space setting. But that's a little hard to prove. You need assumptions for that. But again, under irreducibility and finite state space, as soon as it's not strict, then you've solved the DP equation. You can prove that. That requires a bit more Markov chain theory that I've even taught you, but it's not. It's possible.
Reducibility in the closed loop sense, right?
Yeah, for each, so there is a notion of irreducibility for controlled Markov chains. It's actually in chapter 9 of my book, which you can read if you want. But I mean that, for each n, that guy's unit chain. Yeah,
okay.
Yeah.
Closed loop.
Yeah, closed loop, yeah. Okay, there's more to say, but like I said, there's too much to say. So I'm going to all going to take a deep breath and do the last algorithm?
Two more.
Two more? No, we did value iteration.
We did policy iteration.
And we did policy iteration?
Linear program.
That's it. So we're going to do one more.
I thought we had three.
Three. Value iteration is one.
Right.
We did that. Policy iteration is two.
Yes.
Did that.
Oh, that's
And that's policy iteration. Oh yeah, I didn't say it. Oh my God.
Yeah, about this, I can see why.
Sorry. Oh, I see. That's funny. No. Newton-Raphson is policy iteration. It's identical. Yeah. All right. Okay. So you will see that the next algorithm is ridiculous. I might make you code it. I don't know. So okay, so if I say it's ridiculous, why am I doing this? It's because it's another approach that, if you understand this, you can see another direction for approximations, and it's something that hasn't been explored enough at all. I have a feeling that this might be way more useful than other approaches that are fashionable today. So the reason, this just gives you another tool that maybe you could use in some applications. So the motivation is as follows. I mean, the starting point. So I'm not going to get into the depth, but I can give you some of the main ideas. So we've talked about empirical distributions before in this course. I don't know. We did somewhere. It came up somewhere, didn't it? Maybe not. I'll write it down. Okay, so this is the definition of an empirical probability mass function in this case. Basically, for every x and u, you count up the number of times you visited x and u, the pair x and u, and divide by n. So this is a histogram, of everything. So this is a probability mass function for every n, but it's also a random variable. Okay, and as n goes to infinity, it might not converge, but you can find limit points and stuff like that. So this, we're looking at a finite state in action space. So you can think about this as just a matrix or a long vector, and so it's bounded, so you can find subsequential limits. Okay, so all possible limit points. Okay? So basically, as n goes to infinity, again, it doesn't converge, but we're going to let script g if you like, we'll restrict to inputs for which this converges, and then we look at all limits, okay? But so why would we care about this, everybody? If I take my cost function C and I integrate with respect to this empirical distribution, what I mean by that is the dot product, right? And then you basically go through and look at a change of variables, If you plug this in, you just get the sample path average. That's the whole point of empirical distributions. So it's just about a bookkeeping. Here I'm looking at the fraction of times that I saw a particular x and u, and I take C of xu times the fraction of times I saw that pair. So this exercise, this is exactly 1 over n summation k equals 0 to n minus 1 of C of x k uk. So think it over. It's just bookkeeping. Or it's a change of summation. It's just it's nothing. All right. But you guys should all know this. This is really something that comes up a lot in our world, in machine learning, in communications, and control, everywhere. Empirical distributions, and that's one motivation. All right. Okay. So we care about this because the limits of this are possible costs. So our goal. I might as well be more precise. When I say a subsequential limit, I mean I take a subsequence of the integers that goes to infinity. I look at gamma ni of xu for all x and u, and I assume the limit as I goes to infinity exists. And so there'll be lots of limits. So if this is true, then gamma is in G. I script G. That's my definition of G. And eta star is greater than or equal to, or less than or equal to, gamma C. Right? Yeah. I mean, look, I got a policy. I took any policy. I look at this dot C, which is just a sample path average, and that might not converge, so I take a subsequence that converges, and that's greater than or equal to the optimal. So we get an optimization problem. Yeah, you happy? No, you look like you're concerned. Okay, so we have an optimization problem. All right. Yep.
You say let G be the set of all possible limit points.
And that.
Of what set?
There.
Of that set.
All right. So you give me any input. You give me any input sequence. And by admissible, I mean it doesn't depend on the future. It's like we've just defined before. I look at this sequence of empirical distributions, and then I find every possible subsequential limit which converges. Instead of all possible functions of two variables, I call that G. And what the hell is that? Well, we don't know yet, but based on this definition, I get this minimization problem, and this is going to be equal to eta star. It's got to be. Because I know that if an optimal policy exists, for an optimal policy, I plug it in here, I get the sample path average, that goes to eta star. So I know that I can actually find eta star through the minimization problem. And the question is, what the hell is G? All right. So again,
Here the minimization is over.
some weird set G, and you don't know what the hell it is. So basically what you have to do to write this code, you have to be able to do a simulation experiment, and remember I didn't say it was Markov. There's every possible sequence of inputs, randomized inputs, it could be randomized policies, and then collect together all the possible limits of empirical distributions, and then you gather up this G, which is this weird fractal object, and you perform fuzzy gradient neural network. Okay, now I gotta tell you what G is. So it turns out you can characterize G. Now, the reason I can't get into the math is because I'll have to go through another martingale argument. I'd have to go through, there's some very elegant mathematics, but this is not a math course. I keep telling myself that. But let's figure what this is. So,
Are the math in the handout?
yes. Well, actually, I left it out of this handout. This is only 8 pages long, but this is all taken out of my book, where it's given in very careful detail. And it's not that hard. It's just that we have limited time. You know, it would take a half an hour. We don't have that many half hours. Yeah. I love this stuff. I mean, yeah.
There's no, I can think of in the way the abstraction is written it, clearly I see the LP and stuff, but then there's no reason for G to be convex set, or there's so many things.
Well, yes, there is. Because if you give me, it's obviously convex. Oh my God, you're forcing me to do stuff I shouldn't be doing. If you give me one, that's the beautiful thing about all this stuff. If you give me one input sequence, admissible sequence, and then give me another one, I can at time 0, pick one with probably half and the other with probably half, or something like that. Well, that's not it. But anyway, I can prove it's convex by randomized policies. Yeah. Yeah, that's right. At each time k, I'm going to. That's not it. Anyway, I can't do it right now. But if you gave me 30 seconds, I could give you a proof. But by fooling around with admissible inputs, you can prove it's convex. Yeah. It's pretty amazing. It's not hard at all to show it's convex. So here's what you do. So a starting point is this. Well, I mean, first, gamma is a probability mass function. Right. If you look at the pre-limit, you sum this over all x and u. Then I sum it, I can exchange the sums. If I sum this over x and u, I get 1. And the average of 1 is 1. Yeah. So this is a PMF for each n, so the limit's a PMF as well. So the next first is Bayes' rule. So I'm going to write out gamma of x u equals pi of x. There's just notation if you want. And so basically, this is just a definition, all right? So basically, I can compute the marginal for x, which is also PMF. It's pi is the first marginal of gamma is a part of PMF, because again, that's true here. Initially, if I sum this over u, all right, then I get a PMF over x. Because then I just get an average. I get a sum of indicated functions xk equals u. Xk equals x. So for each n, if I sum over u, I look at the first marginal of this gamma tilde, I'll get a PMF over x. So that's a PMF, and that you can view as a conditional expectation.
That's your stochastic policy.
Yeah. Remember, I'm just saying, given any gamma and g, I want to understand it. I want to put in constraints. The first constraint is it's a PMF. Second constraint is if I look at the first marginal, it's a PMF, right? And then I've got a definition here. That's just a definition. But Bayes' rule would say that that definition is just a conditional probability. So I'm viewing this as a randomized policy. So the probability ut equals u given xt equals x is just given by this phi. And I'm just stating this to you all, that if you gave me any limit of these guys, any of these gammas, I could perform this decomposition, I would obtain a randomized policy. So a major breakthrough here is that, think about this, what I've just said. If I optimize over all policies here, all possible sequences, I go through and I take limits, right? I get this optimization problem. I just told you I don't have to look at all possible input sequences. I can only just look at randomized policies. So without any math, with just blabbing, I've proven that it's optimal to consider only randomized stationary feedback. Again, just by decomposition. I mean, you believe me there. You all agreed that that's basically by making a change of variable in a summation. And you believe it's a PMF, and you know every PMF can be decomposed, And then basically that randomized policy will give me the same performance as the limit.
So for the constraint like pi is also PMF.
Yeah.
But you actually got like feedback u, so pi x is in your set.
Oh no. Gamma is a set of all bivariate. It's really important to change. This definition is crucial. That this G thing is a set of all bivariate probably distributions on x and u. I'm just saying, if you gave me any limit, right, because it's a PMF, I can define a randomized stationary policy, which will give me the same performance. So you came up with some really complex thing that depended on the entire history. You did some ingenious thing. And I'd say, well, haha is on you. I take your limit, I define a randomized stationary policy, and that has the same performance. So the fact that you can prove that state feedback is optimal just by waving your hands is amazing. There's no, it's if you don't use this approach, it's really hard to prove that state feedback is optimal. Isn't that, I mean, come on, it's cool, isn't it?
When you say that it's optimum, you mean that the cost is eta star?
Well, I'm saying that you agreed with me that when I perform this minimization, I will get eta star. Okay? And I haven't characterized what G is. It's some crazy thing yet. But given any gamma in G, it came from some wacko policy you cooked up. You did some deep neural network with tons of history and blah, 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 fuzzy logic. But I'm going to take your the limit of the empirical distribution. I'm going to decompose it, interpret this thing here as a randomized policy. It will have the exact same performance.
You mean the cost that we will achieve will be?
Yeah, we'll get the same gamma, it's gamma.c. Yeah, the limit was gamma.c. This is just...
You can do no better than eta star.
I'll get the same performance, yeah. I mean, right there. I decompose gamma can be written as a marginal times a conditional distribution. Yeah.
But that doesn't mean it's unique too, right? Like,
well,
many other...
No, G's huge. G's huge. No, I'm just looking at one possible limit. Some of them will be terrible. Yeah. G's a giant set. Yeah, but I'm just saying any gamma in G can be decomposed. So I guess there's a gap here that I don't know that when I run this randomized policy, I really will get gamma back again. But that's the martingale stuff. That's where there's some martingales and stuff that come in. You've got to justify that. But so if I apply, it is true that if I apply this randomized policy, I will get gamma back again. And it's quite easy to prove, but you need to know what a martingale is.
As an algorithm?
Yeah. We haven't gotten there yet.
Yeah, okay.
We're almost there. Do you think we can do it? What time we kicked out of here? On Thursdays?
We've got plenty of time.
All right, plenty of time. So this can die now, I think. Yeah. So, So here's the thing, though. So next, I go at first there, second. I'm just iterating just what I just said to you. That, I got gamma through some crazy policy, but then if I define this randomized policy from gamma, and I apply it, I'll get the same gamma back. And that's a simple martingale argument, but I'm not going to give it to you. And thirdly is that pi is invariant for the resulting transition matrix. So I remember I had my piece of phi before for a stationary deterministic policy. So here I'm generalizing that definition. So for every x I sum over u, the probability I'm going to take the action u times the probability, given u and x of going to y. So that's the transition matrix. And pi is stationary. That pi there is stationary for p phi. All right, for the same gamma, So throughout this, I took one gamma from G, and I'm getting properties, all right? And you know what the proof is? I'm not going to prove it. The proof is that I can replace n by n plus 1. Basically, I replace ni by ni plus 1, and it goes to the same thing. And you interpret that. It really is that simple. Basically, basically I'm shifting all the k's by 1, and I get the same limit. Yeah, and then you end up getting this invariance equation. All right, so we're almost there. In fact, that's it. So this is actually called, this is equation 915 for my book. So you know, if you want the details, they're in this book. So chapter 9 is where all this stuff is. And so here's a proposition. So first of all, G is a polyhedron. You know, it's a subset of a big polyhedron because every gamma in G is a probably a mass function. And it's characterized by these constraints. So first of all, any gamma in G has to be non-negative. It's a probability mass function. And again, it's a probability mass function. And so it sums to 1. And the invariance property is really nice. So what does it mean to be invariant? This has another representation. So pi, I'm going to write this out longhand, I think. So how do I say this again? I'm going to rewrite this in a way that doesn't have pi in it. And so what?
Can we use a trick from my homework?
I'm trying to explain it to you. No, it's something like that. I'm trying to explain it to you. I don't need help. It's just I'm trying to get my thoughts together. So don't help me. So this P phi is a sum over U, and that thing there. So I'm saying pi phi equals pi. You notice that if I take this and multiply it by pi, I'll get pi times this little phi. So I'll just write down. Okay, so that's how I define the first marginal. I call it pi, right? So the summation over U of gamma is this sum over here, because that is precisely this. You just write it down. Again, forget it. Just trust me. Like I said, I'm not going to prove everything, but this and this are identical things. Again, look at the definition of P phi. It's a sum over U of phi U given x, P U x to y, right? For this, I've got to multiply both sides by pi of x. And pi of x times phi U given x is this gamma. I retrieve gamma again. So this is just a rephrasing invariance. But it's phrasing invariance for the bivariate distribution instead of univariate. And that's it. That's it. So there's your LP. So I basically want to minimize gamma.c subject to the sum of the entries is 1 and this crazy linear constraint. It's massive linear constraints. And I've never had the nerve to ask anyone to code this, but now the computers are so fast, what the hell, let's do it. But so the problem, of course, h of x, I mean h, let's call it h star. So if there are d states, then the value function is a d-dimensional vector, right? But this gamma star, when you optimize this, you're going to get a gamma star. And gamma star is viewed as an element of R d times whatever we've called it. I don't know what we've called it, m, if they're m states. So we've got this big explosion in complexity, in terms of the number of variables. The vector's gotten much larger. But it's a beautiful convex problem. I mean, well, the original thing is this horrible fixed point equation. So we have, and this is a theme, everybody. Theme alert is that it's really typical.